A glacier once dumped boulders into the sea at the equator. Not off a mountain, not at altitude. At sea level, in the warmest belt of the planet, ice was grinding across the ground and dropping rock into salt water. In a cliff in northern Namibia, you can put your hand on the moment it ended. Below your thumb, glacial rubble. Above it, pale limestone, the kind that only forms in shallow tropical water. Between them, nothing. No transition, no weathering, no gap. A line you can cover with your thumb. And it isn't one cliff. The same stack, glacial junk with warm water carbonate slapped straight on top, shows up in Australia, in Canada, in Ethiopia, in China, in Siberia. Every continent that has rocks of the right age has it. The tropics are the last place on Earth to freeze. So if the equator was under ice, everything colder than the equator was under ice too. Whatever holds this planet's temperature inside a livable band didn't wobble that day. It failed. Keep that line under your thumb somewhere in mind. It comes back at the end of this, and by then it says something different. If that bothers you the way it bothers me, subscribe and leave a like, because that's the only signal that tells me to keep making these long. And put your city and your local time in the comments. On the planet you're about to walk across, the sun still came up every morning, right on schedule, and it changed nothing. Start with the rubble, because that's the part you'd walk past without looking. Geologists call it diamictite. You look at it and you see boulders the size of a chest freezer sitting in mud, with pebbles and sand and grit jammed in around them. Nothing sorted by size, nothing lined up. Water can't do that. Moving water is a sorting machine. A fast current carries the big stuff and drops it first. A slow current carries only the fine stuff and takes it further. You end up with gravel here and silt over there in tidy beds.
Diamictite is concrete with the gravel left in. Everything from dust to boulders, mixed together, dumped at once.
Ice does that. Ice doesn't sort anything. It bulldozes whatever it touches and lets the whole load go where it melts. By itself, that isn't proof. Mud and rock avalanching down a steep underwater slope makes a very similar mess. So you look for a drop stone. You want a patch of old seafloor that settled slowly, in lamina a millimeter thick, flat and undisturbed, the sediment equivalent of dust on a shelf. Then you find a single, fist-sized rock sitting in the middle of it, with the layers underneath bent down and the layers above draped over the top. Something delivered that stone out of the water column onto a quiet seabed hard enough to dent it. Out in open ocean, there's exactly one delivery service that does that. An iceberg, floating, melting, letting go of what it was carrying. Then there's the ground itself. In parts of Australia and Namibia, you can stand on the actual surface a glacier crossed.
It's polished smooth and it's scratched. Parallel grooves cut into solid bedrock, all running the same direction, straight under your boots and out the far side of the outcrop. And you can follow them for an hour and they still point the same way. That's what happens when a rock held in the base of an ice sheet gets dragged for miles with a few hundred meters of ice pressing down on it. Those three things sitting together are not ambiguous, and they sit together on every continent in rock that formed within a few degrees of the equator. Ice reached the equator at sea level. There's other freight in these sequences that nobody ordered too. Bands of iron ore sitting inside the glacial rock in Canada and South China and Namibia. But the thing that stopped people cold was simpler and dumber than that. It was the limestone. The first person to take that sandwich seriously had spent a good part of his life on ice. Douglas Mawson led an Antarctic expedition in 1912 that went catastrophically wrong. One man went into a crevasse with most of the food and the best dogs. The second died on the way back. Mawson finished the journey alone, hauling a sledge he'd sawn in half, the soles peeling off his boots and the skin peeling off his body, and got to the coast in time to watch his ship leave. Then he went home to Adelaide and spent decades mapping the Flinders Ranges. Dry hills, spinifex, heat coming up off the rock. And he kept finding the same thing in stone, hundreds of millions of years old. Boulder beds. Glacial boulder beds. In 1949, he put his name to the argument in public. There had been a great ice age before the Cambrian. It had been enormous, and it had reached ground that had no business ever being cold. To be fair about how that landed, it landed as an eccentricity from a national hero. 15 years later, a Cambridge geologist named Harland made it much harder to wave off. He'd worked Svalbard. He'd read everything anyone had published on these rocks, and he went through the reports one landmass at a time. Norway, Greenland, Africa, Australia, North America. His point was about pattern. These deposits aren't scattered through deep time the way ordinary ice ages are. They cluster. The same interval, just before the Cambrian, over and over, on continents that now sit on opposite sides of the world. Then came the measurement that should have settled the whole thing, and didn't. A compass needle doesn't only point north, it also tips. Stand in the tropics and it lies almost flat. Walk toward a pole and the north end dives toward the ground, steeper and steeper, until above the pole it hangs straight down. Iron-bearing grains settling out in mud do the same thing. They swing into line with the magnetic field of that day and then get locked in place when the mud hardens into rock. So measure the tilt frozen into an ancient rock and you get the latitude it formed at. Not the direction it's facing, the latitude. The glacial rocks came back flat, low latitude, tropics. The cleanest signal of the lot came out of a formation in South Australia called the Elatina. Nobody could win this argument at the time, and it wasn't their fault. Continental drift wasn't accepted machinery yet. Plate tectonics only arrives at the end of that decade. Without it, telling people that a rock formed at the equator and now sits in the Arctic isn't an argument, it's a puzzle with no board to play it on. And even after tectonics landed, the magnetic evidence had a soft joint in it. Hot fluids moving through the crust during mountain building can reset a magnetic signal in rocks thousands of kilometers from the nearest mountain. And separating an original signal from a reset one takes slow, mineral by mineral work. So the field had two doors in front of it. Behind one, the entire planet froze solid. Behind the other, something is wrong with the rocks, or with the latitudes, or with both. It spent the next 30 years going through the second door. In 1974, a Dutch geologist published a monograph on these deposits that ran well past 100 pages. He'd spent years mapping in Angola, in a country full of exactly this kind of chaotic boulder bed, and his case was patient and specific. Nearly every feature people were calling glacial can be made by mud and rock sliding down a steep underwater slope. Poorly sorted? Debris flows are poorly sorted. Big clasts floating in fine matrix? Same. Scratched stones? Rocks grind each other in a moving slurry. And the association everybody found so damning, glacial rock wedged against warm water carbonate, he simply turned around. Carbonate platforms form in warm water, so those rocks are telling you the climate was warm, and the boulder beds are telling you the slope was steep. Tectonics, not weather. That was a real argument, made in good faith, and it stalled the field for years. The second patch was stranger. If you don't want a frozen tropics, there's another way to get ice at low latitude. Tip the whole planet over. Push Earth's axial tilt past about 54 degrees, and the arithmetic of sunlight inverts. The poles roast in summer, the equator becomes, averaged over the year, the coldest ground on the planet. Sea level ice near the equator stops being a paradox and turns into the expected result. It's an elegant piece of work. It also asks you to accept that Earth lay on its side for most of its history and then, right about the time animals show up, quietly stood back upright and has stayed upright ever since. There's no accepted mechanism for that second half. The moon holds our tilt where it is, and shedding that much of it inside a couple of 100 million years is not something anyone has managed to make work on paper. A third option: leave the tilt alone and move the pole instead. True polar wander where the whole solid Earth rolls relative to its spin axis and tropical rocks end up recording a polar climate. That does happen in small amounts. Getting it to cover this job needs a lot of it, fast, and more than once. And a fourth, which lasted longest and still has defenders. These are ordinary local glaciers in local basins. Rodinia was tearing itself apart at the time. Rifting produces deep troughs with high shoulders. Put mountains on the shoulders, glaciers on the mountains, dump the debris into the trough, then repeat the trick down the length of the rift as it unzips over tens of millions of years. You'd get glacial deposits at many latitudes and many different dates that only look worldwide and simultaneous because your dating is too coarse to tell them apart. What killed the patches wasn't one paper. It was accumulation. The striated pavements are the wrong shape for debris flows.
A slurry scratches stones. It doesn't polish a plane hundreds of meters across and rule every groove on it parallel. Drop stones in undisturbed lamination can't come out of a slurry either, because a slurry destroys lamination on its way past. Uranium-lead dates on volcanic ash beds got sharper and sharper, and the ages stopped drifting apart. Glacial rock on cratons thousands of kilometers from each other turned out to sit inside the same narrow window, starting together and ending together. Local basins don't do that, and the Elatina magnetics kept surviving every test thrown at them. It formed within a few degrees of the equator, and it saw ice. There was one detail in those same Australian rocks that everyone had a comfortable answer for. Fine laminae, rippled, stacked in rhythmic bundles that thicken and thin. Obviously varves, seasonal layers, the annual freeze and thaw of a glacial lake, one couplet per year. That reading sat there unchallenged for decades. Meanwhile, the machinery that made all of this possible had already been published. Not in a geology journal. Nobody in the argument was reading it. In 1969, a Soviet climatologist named Mikhail Budyko put out a simple model of Earth's temperature. An American published something close to it the same year independently. The models were crude on purpose. You slice the planet into latitude bands, you balance the sunlight coming in against the heat radiating out, and you let warmth flow from the warm bands into the cold ones. Then you make exactly one thing depend on temperature. If a band gets cold enough, it's covered in ice, and ice is bright. That last piece carries the story. Park a white car and a black car side by side on a July afternoon, come back in an hour and lay a hand on each roof. Same sun, same air, same hour. All that differs is how much of the light the surface sent back. Open ocean drinks up nearly everything that lands on it.
Snow-covered ice throws nearly everything away. So ran the model cold. Ice creeps down out of the poles. The bright band widens, the planet absorbs less. It cools further, the ice creeps further still. Every step makes the next step easier to take, and Budyko's arithmetic said there's a point of no return. Get the ice edge down to somewhere around 30 degrees of latitude, the line through Cairo and New Orleans and Shanghai, and the feedback outruns everything holding it back. From there, the model doesn't find a new balance slightly further south. It goes to the equator, all of it, fast. The part people still underestimate is that it isn't a dial, it's a switch. There's a stable warm Earth, and there's a stable frozen Earth, and the ground between them is a slope you can't stand on. Now, everybody knew this couldn't be right, and they had a decent reason. Carbon dioxide gets pulled out of the air by rain landing on rock.
Rain is faintly acidic. It attacks silicate minerals. The products wash down to the sea, and the carbon ends up locked into carbonate on the sea floor. In 1981, James Walker and his colleagues spelled out what that means across geological time. The reaction runs quicker when it's hot and wet, and stalls when it's cold and dry. Warm the planet up, the drawdown accelerates and hauls carbon out of the air. Cool it down, the drawdown stalls, volcanic carbon piles up, and the planet warms back up on its own. That's a thermostat, wired into the rocks, running for billions of years. And it was taken as proof that a runaway freeze was impossible. The planet self-corrects. Budyko's frozen state was an artifact of a model too simple to contain the fix.
The physics that predicted a frozen Earth was published in 1969. It got filed as a flaw in the model. It took until 1992 for someone to notice that the thermostat doesn't argue against a snowball at all.
It explains how one ends. Joe Kirschvink was a paleomagnetist at Caltech, which meant he'd handled the low-latitude glacial signal himself. His contribution was 2 pages long, buried inside a fat, multi-author volume about Proterozoic life, and it did the one thing nobody had bothered to do. It put the climate modelers' runaway, the geochemists' weathering feedback, and the geologists' tropical boulder beds into the same argument. Freeze the planet, and the carbon sink switches off. The volcanoes carry on regardless. That's the way out, and it's still the only one anyone has found. He gave the state a name, and the name stuck. Snowball Earth. Look at what happened there. The geologists had rocks they couldn't explain and spent 30 years explaining them away. The climate modelers had a mechanism they couldn't believe and spent 20 years apologizing for it. Both halves were in print, in libraries in the same cities, and what the problem needed was one person who read both literatures walking down the hall. Which means the frozen Earth was never really discovered. It was derived, printed, and thrown out as a mistake more than 20 years before anyone thought to hold it up against a rock. So what does it take to shove a planet over an edge like that? Less than you'd hope if the planet is already standing close to it. And around 720 million years ago, this one was standing very close indeed. Begin with where the land was. For most of Earth's history, the continents have been spread through every latitude, some baking on the equator, some parked near a pole. At this point, they weren't. Almost all the land on the planet was welded into a single supercontinent, Rodinia, and Rodinia lay draped across the tropics. Then it began to come apart. Cut a loaf of bread into 8 pieces, and you haven't changed how much bread you have. What you have enormously changed is how much crust there is. A continent works the same way. Split one landmass into a dozen, and you manufacture edges. New rifted margins, new highlands along the rift shoulders, fresh, unweathered rock hoisted up into the open air. And every bit of it in the warm belt, where the rain comes hardest and hottest, which is exactly when rain eats rock fastest and pulls the most carbon out of the sky. The thermostat hadn't broken. It was being fed something it had never been fed before. Every fresh surface the rifting exposed was one more mouth on the carbon dioxide supply. Then came the eruption. About 719 million years ago, an immense volume of basalt forced its way up through the crust of what is now the Canadian Arctic. Baffin Island, Ellesmere, Victoria Island, running west into Alaska and east into Greenland. Geologists call it the Franklin Province, and there are sills from it you can walk along today in country where nothing grows. At the time it erupted, those rocks were sitting on the equator. The kind of rock matters here more than anything. Granite gives up its minerals slowly. Basalt is loaded with calcium and magnesium in forms that break down fast, and calcium and magnesium are exactly what carbon needs in order to be locked into stone and taken out of circulation. Spread a continent-sized sheet of fresh basalt across the wettest, warmest zone on the planet, and you have installed the most efficient carbon sink Earth knows how to build. Now the timing. High-precision uranium-lead dates on the Franklin rocks put the main pulse of that eruption less than 2 million years before ice starts appearing in the record. For an event that ran for the next 50 million years, that's the trigger and the shot arriving on the same afternoon. There's a rival version of the same eruption that doesn't need weathering at all. Fissure eruptions on that scale throw sulfur high into the atmosphere, and sulfur droplets are mirrors. They bounce sunlight back for a few years, then rain out. Normally that buys you a cold decade and nothing more. But over the tropics, where the sunlight is strongest, above a climate already running cool, with the ceiling of the atmosphere sitting lower than it does in a warm world, eruption after eruption could have driven the temperature down hard and fast. Faster, crucially, than the weathering thermostat can respond to anything. Slow poison or a punch to the jaw. The argument isn't settled, and both may have been happening at once. Either way, the geometry is the cruel part.
Rock weathers fastest in the tropics. Ice reflects the most sunlight in the tropics because the tropics are where the sunlight is. Whatever was dragging the temperature down was doing its work in the same band of latitude where the runaway, once it arrived there, would be most violent. The trigger and the trap sat on top of each other, and once the ice edge came down through the subtropics, there was nothing left to argue about. The planet had a new surface.
Picture what that actually meant, because it isn't the version on the Christmas card. Averaged over the whole globe, the models put the surface about as cold as the interior of Antarctica is today. That's the mean for the entire planet, poles and equator together. Over the ocean, ice grew downward until it hit a floor it couldn't get past. Heat is always leaking out of Earth's interior at every square meter of seabed, and that heat has to go somewhere. So the ice thickens until the warmth rising from below balances the cold pressing down from above, and then it stops thickening. In the models, that balance point comes out at roughly a kilometre down. The ocean beneath stayed liquid the whole time. It simply lost the ability to talk to the sky, and the weather turned inside out. On our planet, the tropics are the engine room. Warm water evaporates, rises, and comes back down as rain. That engine runs on a warm sea surface. Seal the sea under bright ice, and it has no fuel. What's left is a thin, strange circulation in which the equator becomes the driest place on Earth. A desert made of ice, where the surface doesn't melt so much as evaporate into the air, molecule by molecule, and the wind carries it off. That means ice was disappearing at the equator continuously. Whatever it lost there had to be replaced from somewhere, and the somewhere was the poles. So the flow ran backwards. The thick ice at high latitudes, under its own weight, spread toward the equator. The way honey poured onto a plate slumps outward and thins as it travels. One sheet across the entire world ocean, creeping toward the warm end and vanishing when it got there. Stand on it. Noon, on the equator, sun directly overhead. The sky is clear because there's almost no water vapor left in the air to build a cloud with, and nothing comes out of that sky. Under your boots, there's no snow, just hard blue-white ice, scoured and ridged by wind, and it is moving, slowly, toward the horizon. About a kilometer straight down, there's an ocean, and you have no way of reaching it. Your breath freezes into your collar. Nothing smells of anything, because nothing anywhere is warm enough to give off a smell. Underneath, in the dark, the chemistry was quietly changing. An ocean that can't trade gases with the atmosphere runs out of oxygen. What's there gets used, and nothing replaces it. And once seawater goes anoxic, iron starts behaving completely differently. Instead of rusting out of solution the instant it appears, iron dissolves and stays dissolved. Hydrothermal vents on the seabed kept feeding it in from below for millions of years, and it accumulated. An entire ocean slowly loading itself with iron, the way it hadn't done since the first billion years of life. That's what those iron beds in the glacial rock are. At some margin, somewhere, that loaded water finally met oxygen and dropped its whole cargo out of solution. A deposit type that had been absent from this planet for something close to 1 billion years came back inside the ice. The iron carries a temperature signal too. Isotope work on those beds points to seawater colder than anything else anyone has ever measured in the rock record. The ocean was sealed. All of it. Not perfectly, because nothing in geology is ever perfect. With the ice evaporated away in the low latitudes, it left behind whatever it had been carrying inside it. Grit, volcanic ash, dust blown off bare ground, all of it concentrating on the surface as the clean ice around it went into the air. Under all of that sits the objection that nearly killed this whole idea. Photosynthesis needs light. A kilometer of ice does not pass light. And the record is blunt about one thing. Eukaryotes, the lineage of complex cells that eventually produces everything you can see without a microscope, are present before this happens and present afterward. Algae, protists, cells with nuclei. They didn't restart from nothing. They went through.
For years, that was the strongest single argument against the hard freeze, and it deserved to be. If your model kills the biosphere, and the biosphere is plainly still there, your model is wrong somewhere. The most promising answer was lying on top of the ice the whole time. Leave a dark coin on a snowfield on a sunny day and come back an hour later. It's gone, under the surface, sitting in a small, water-filled pocket it melted for itself. Dark absorbs, white reflects, and a coin becomes a tiny engine. Now scale that up to a planet, dust and ash gathering on ice that's evaporating out from under it, with the sun straight overhead. Every dark patch sinks its own hole. The hole fills with meltwater. The water sits at the freezing point inside walls of ice that are far, far colder than that. Those are cryogenite holes, and they aren't hypothetical. They exist right now. A team of scientists went and sampled the surface of the McMurdo ice shelf in a stretch of Antarctica that the men on Robert Falcon Scott's expedition, passing by in 1903, called the dirty ice. In places, there the shelf freezes right down onto the sea floor, picks up sediment and whatever was living in it, and then the wind strips clean ice off the top over the centuries so that seabed material rides slowly upward until it's out in the open. You can walk across an ice shelf there and come across a marine sponge lying on the surface, in the air, a long way from anywhere it could have grown. In the ponds that form in that debris, the team found eukaryotes. Not in most of them, in every single pond they sampled. Different communities in different ponds, sorted largely by how salty the water was. Microalgae, protists, small animals, entire crowded little worlds a few paces across and knee-deep. That's a modern analog. It isn't a fossil, and it shouldn't be treated as one, but it means the refuge isn't a hopeful wave of the hand. It's a habitat you can go and stand in today and take samples out of. There's a second one further down, and it's a dark one. Where an ice sheet sits grounded on rock, pressure and heat from the earth melt its base, and that water drains out into the sea carrying oxygen locked up in the ice. Push oxygenated water into an anoxic, iron-loaded ocean, and you get a chemical edge. A chemical edge is a power supply. Microbes have been making a living off exactly that on the modern seafloor for as long as anyone has looked. So there were places to be, small, cold, scattered, dark-rimmed places, none of which settles the larger argument, and pretending otherwise would be cheap. There's a rival picture, the slush ball, in which a belt of open water survived in the tropics the whole time, and everything about a sealed ocean is too extreme by half. It solves the biology instantly, which is exactly why it's attractive.
What it can't do is explain the rest. Open water soaks up sunlight and breathes carbon dioxide back out, so a slushy planet should climb out of its glaciation quickly and gradually. The rocks show the reverse. These glaciations lasted an absurd length of time, and they ended sharply. And they ended everywhere at once. Hard or slushy, though, the way out was the same, and it was not quick. The escape route is almost insultingly simple. It's the waiting that's monstrous. Volcanoes don't care what the weather is doing. Arc volcanoes, rift volcanoes, the ridges running down the middle of the ocean basins, all of them kept exhaling carbon dioxide all the way through the freeze. And the process that normally takes it back out, rain landing on exposed rock, was gone. There was no rain worth the name. There was almost no exposed rock. The drain was under ice. A tap left running with the plug in. A slow tap, though, and a deep tub. At anything like modern outgassing rates, the atmosphere gains carbon at a pace that means nothing across a human lifetime, and everything across a geological one. And the level it has to reach is savage, because it's fighting a whole planet's worth of mirror. The rocks and the models both land near 350 times today's carbon dioxide before the ice at the equator will start to give. That's the trap closing on itself. The same brightness that dragged the planet into the frozen state is what forces the air to load up that far before it can climb back out. Small things help at the edges.
The dust and ash piling up on the tropical ice darkens it, and dark ice absorbs more, which lowers the bar. One set of models has the first surrender happening nowhere near the equator, up in the middle latitudes, where less snow falls to keep refreshing a clean, white surface, and old, dirty ice gets left alone to bake. There may be a reason the tub filled so slowly the first time.
Once Rodinia's fragments had drifted and the ocean floor between them had grown old, cold, and deep, the mid-ocean ridges, the single largest steady source of volcanic carbon on the planet, appear to have been running at an exceptionally low rate through this exact window. Less gas going in, a longer wait. And then there's the wait itself. The first of these glaciations, the Sturdian, lasted 57 million years. 57. The whole stretch from the last dinosaur to your kitchen this morning is only a little longer than that. The second, the Marinoan, ran roughly 4 million. Same planet, same mechanism, near enough the same continents, and the two runs of the experiment came out more than 10 times apart. There's no agreed explanation for the difference. And this is the point where I have to take something back. I've spent this whole stretch describing one long, continuous winter. Freeze, wait, thaw. That's the shape the field has worked with since Kirschvink, and it's the shape the rocks appeared to demand. In 2026, a group at Harvard published a model that won't hold that shape at all. Couple the climate properly to the carbon cycle they find, and the system doesn't sit frozen for 57 million years and then leave. It oscillates. Carbon builds until the ice retreats, the planet flips over into a hothouse, and the instant it does, all that fresh basalt is standing in the rain again. The sink reopens, carbon crashes, the ice comes back. Then it happens again. A pot lid on a boiling pan, lifting and dropping and lifting. If that's right, the 57 million years was never one winter, it was dozens of them, with hothouses in between. And the reason an oxygen-breathing biosphere walked out the far side is that the lights kept coming back on, over and over, long enough each time for photosynthesis to restock the air. Take any one of those thaws and slow it down, because the ending is the part the rocks record best. The instant open water appears anywhere in the tropics. The loop that closed the planet down runs backwards, and it runs just as hard. Everything that took millions of years to assemble comes apart fast. Models clear the ice off the planet in a couple of thousand years. Some do it quicker. Think about where all that water went. Ice stacked kilometers deep on the land and a kilometer deep across the sea went back into the ocean over a span shorter than recorded history. Sea level came up at something close to 100 times the rate it's rising today. Coastlines didn't retreat, they ran. We know that number because of those laminated Australian beds, the rhythmic ones, the ones everybody had filed as annual lake varves for decades. A team went back to them with a different question. Not how many years are stacked in this pile, but how deep was the water while it was forming? Ripples answer that.
The shape of a wave ripple is set by the orbital motion of the water passing over it, which is set by the depth above it, and wave tank experiments have pinned that relationship down precisely. And the fine paired laminae between the ripples turned out not to be seasons at all. They're tides. One couplet per tide, bundled into the fortnightly spring and neap cycle, which makes the rock a calendar with 2-week resolution. Read that way, the pile stops being a slow lake and becomes a stopwatch. The entire stack went down in about a century, and the water depth over that seabed barely changed from the bottom of it to the top. Sediment was arriving at a berserk rate, and the seafloor never got any shallower because the ocean was climbing as fast as the mud could fill it. The weather matches. In rocks of this age on several continents, there are wave ripples you could sit down inside. Crest to crest, they're bigger than anything the modern ocean builds in shallow water.
A hot, wet, violently unstable atmosphere over a newly opened sea with no ice left anywhere to calm it down. Then the rock changes completely. Sitting directly on the glacial rubble, with no soil, no gap, no transitional bed of any kind, there is carbonate. Tens of meters of it, sometimes far more, the same package in Namibia, in Australia, in Brazil, in South China, in Death Valley. Pale dolostone,
the deposit of a warm, shallow sea laid flat against the leavings of an ice sheet. It's a kettle problem. Boil hard water long enough and the inside of the kettle furs up because heat drives dissolved carbonate out of solution and plates it onto the metal. Now run that at the scale of an ocean. The air at the end of the freeze was loaded with carbon dioxide, so the rain falling on the newly bared continents was acidic, and it was falling in greenhouse heat onto rock that ice had ground to flour and never let weather. Continents went into solution. The sea took on more dissolved carbonate than it could carry and dumped the surplus onto every shelf on the planet in a hurry.
The man who assembled all of this wasn't looking for it. Paul Hoffman went to Namibia in 1993 to work on something else entirely: mountain building, colliding cratons, the assembly of Gondwana, technical, unfashionable work. What stopped him was a contact he kept walking into out in the field: glacial rubble, and lying straight on it, tropical platform carbonate. He rebuilt his entire research program around a thing he tripped over. 50 months of field seasons in that desert, and he was still going out into it in his late 70s. On that shore, while it's happening, the sun is out, and it's the first sun in a very long time that means anything. The air is thick and wet, and it doesn't cool off at night. It's raining, and the rain tastes sour, like flat soda water. The sea is brown with rock flour, and it comes up the beach a hand's width every year, close enough that you could scratch a mark on a boulder and watch it drown.
Out past the surf, the last icebergs on Earth. And under your boots, the mud is turning into limestone. In a few thousand years, all of it was gone. The ocean that came out of that was not the ocean that went in. Everything the ice scraped off the continents ended up in the water, and rock flour is fertilizer. The part that matters most is phosphorus. It's the nutrient that limits life in the sea more than any other, because nitrogen can be pulled out of the air by the right bacteria, but phosphorus only ever comes off rock. For roughly 1 billion years before this, the open ocean had run on bacteria, cyanobacteria mostly. They're small, they're efficient, they can make a living on almost no phosphorus at all, and while they hold the table, nobody else gets a seat. Eukaryotic algae are bigger and hungrier, and they'd been around in the margins for a very long time without ever taking over anything. You can watch the handover happen in molecules. Cell membranes are built with steroids. Different groups of organisms build distinctly different ones, and those molecular skeletons survive in rock for hundreds of millions of years. Run that record forward, and the algal signal is negligible, 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 and then, in the narrow, warm interval between the two great freezes, it climbs and never comes back down. Planktonic algae take over primary production of the world ocean, and they've never given it up since. A field that had been farmed on scraps finally got manured. The consequences run up the chain. Big cells feed things that eat big cells. In that same interval, the molecular record picks up the first traces of sponges and of predatory single-celled hunters that swallow other cells whole. Longer food chains, more energy reaching the top, bodies that can afford to be large. There's another payout that may be even bigger, and it comes with a warning label on it. Ice sheets are the most effective erosion machine this planet has ever had. One group has argued that these ones stripped an average of 3 to 5 vertical kilometers of rock off the continents worldwide. That would explain the great unconformity, the unnerving surface in the Grand Canyon and 100 other places where flat, young sedimentary rock lies on top of far older basement, with everything that should be in between simply absent. A paper out this year makes the case that tectonics explains the pattern better and that the timing doesn't work. It's an open fight. Now, the chain I've just built for you is seductive, and I'd rather break it myself than have you find the crack later. Freeze the planet, scour the continents, flood the ocean with nutrients, get algae, get sponges, get animals, get you. It's tidy, everybody likes it, and the last link doesn't hold. The Ediacaran organisms, the first large, soft-bodied, unmistakably complex living things,
Fronds and discs and quilted shapes, some of them as tall as you are, turn up well after the cryogenian is over. There's a later glaciation, the glaciers, that used to be told as the immediate trigger for them. Then, high-precision dating went through the Newfoundland sections that record it. The glaciers lasted under 500,000 years. That isn't a snowball. It isn't in the same category as a snowball. And the first big Ediacaran fossils in those very same rock sections show up something like 9 million years after the ice was gone. 9 million years isn't a trigger, it's a gap. So the honest version is weaker than the tidy one and more interesting. The freezes didn't manufacture animals. They rebuilt the chemistry of the ocean and the bottom of the food web, and then a very long time went by, and then animals happened in the ocean that was left. Cause at one end, contingency at the other, which leaves the part of this that isn't about the past at all. The thermostat that everyone once thought made a frozen Earth impossible is real. That part isn't in doubt. Over the long haul, it has held this planet inside the band where oceans stay liquid. It works. It works on a scale of hundreds of thousands of years. There's the catch. It isn't a break you can stand on. It's a repair crew that turns up long after the accident, does excellent work, and has no opinion whatsoever about the people who were in the car. Everything the cryogenian did to this planet happened while that thermostat was running perfectly, doing precisely what it does on its own schedule. And underneath that sits the harder fact. Earth's climate isn't one setting with some wobble around it. It has more than one stable state, and there's a road between them. A world with open oceans and a world sealed in ice are both valid solutions to the same physics, and this one has been both. None of that is a warning about the present, because the circumstances aren't the same, and dressing it up as one would be dishonest. The sun is brighter now than it was then, which lifts the flaw considerably. The continents aren't stacked across the tropics anymore. Freezing this planet solid today would take vastly more than it took 700 million years ago, and nobody serious is suggesting otherwise. The lesson that does survive the difference is the one that never needed a snowball to be true. The feedbacks in this system can take a push and run with it, and the correction arrives on a timescale that belongs to rock rather than to anyone waiting for it. Which puts you back in front of that cliff in Namibia, in front of a line you can cover with your thumb, with the coldest the planet has ever been on one side of it and the hottest on the other. We know that because somebody went and looked, not with a satellite or a probe, but with a hammer, a notebook, and season after season of walking the same dry hills. The evidence for the most extreme thing that ever happened to this world is lying out in the open, in a country you can fly to, in rock you can put your hand on. Most of what we know about the deep past is like that. It was never hidden. It was just standing there, unread, waiting for somebody stubborn enough to notice that the story it told made no sense. If you got this far, hit like and subscribe.